Hello everyone, we are here to present our term project for the course of Vibration and Noise Control. Our topic for the project is Tune Mass Damper for Skyscrapers. Firstly, let me introduce my teammates. This is Srichan, this is Manideep Reddy and myself Nandavardhan Reddy. Now let us go through the project setup. This is the simplistic working model of our skyscraper. Now this base can be considered as the ground and the structure here can be considered as a skyscraper. And now in our project we'll demonstrate how different masses will affect the level of dampening. Before seeing this demonstration, firstly let us find what is tune mass damper and how does it affect our lives.
Fuel mass dampers. Before actually speaking about these fuel mass dampers, first let us understand what is their purpose. So when we look into our real world, there are so many buildings, structures, and skyscrapers, and the safety of these buildings and the structural stability of these buildings is very, very crucial in case of emergency or the natural disasters such as earthquakes. So that is when fuel mass dampers come into play. The role of fuel mass dampers is optimizing the structural stability. And in this presentation, we will explore the principles and also the applications of the tune mass dampers in controlling the structural vibrations and how they enhance the safety of the building. Coming to the principles of the tune mass dampers, they are dynamic vibration absorbers which are designed to reduce the amplitude of structural vibrations. They consist of a mass, string, and a damper system which operates at a specific resonance frequency to counteract the oscillations of the building. Below, we can see the diagram of the damper system consisting of masses and strings. Coming to the application, tune mass dampers are widely used in various structures such as skyscrapers, bridges, and wind turbines to control and reduce the effects of wind-induced vibrations and also the seismic vibrations caused by the earthquakes. And here we can see the working of this tune mass damper in this video. So this is a frequency diagram, or we can say a simplified version of the tuned mass damper working model that we have seen in the previous slide. So when the structure is vibrating, the tuned mass damper moves in the opposite direction, counteracting the oscillations of the structure. Therefore, it reduces the vibrations of the structure and maintains the stability of the structure or the building, whatever. So now let us go to the actual demonstration of the working model that we made and let us see how it performs.
Now let us try to simulate our working model under earthquake conditions and we'll see how the vibrations are induced into the system. Now this is how our system behaves when vibrations are induced without any mass. Now we shall try by adding on some damping mass. Firstly we'll add this one, and this one is roughly around 10 grams, and we shall see if this is sufficient to stop the vibrations. We have added a mass of 10 grams, and now let us see how the system behaves. We can observe that the structure is vibrating slightly less, and a lot of vibration is going to the damping mass, and we need to see how increasing this mass affects the behavior of our structure. Now we shall try with the increased mass. So this is roughly around 20 grams, and now we shall see how the system behaves with this. So now we have added a mass of 20 grams, and now we shall see how this affects the level of damping. It's really hard to observe much difference between the previous one and this one, but the next one we shall try with a higher mass and we shall see more effect of dampening. And this one is approximately 50 grams, and we will add this to our system. After some effort we were able to add this. Now Chan will shake this. Now we can observe that the dampening effect has increased when compared to the previous masses. So this can be illustrated as a simplistic working model in order to see how tune mass damper works. Throughout this process, we tried to induce vibrations of similar frequency, but there might have been human errors.
Now Mandeep will take over and explain the equations of motion and maths behind this.
Hello everyone, my name is Manideep. Today I will be presenting the mathematical simplification of the tuned mass damper that we have just seen. So we start by assuming that the working model as a cantilever beam by the fact that the displacement gradient at the ground can be assumed as zero, or it is zero, and also the mass attached at the top of the working model uh, in the case of damping can be assumed as a pendulum attached to the cantilever at the top. So and also the system parameters we can see the mass of object attached at the top as m, small m, and linear mass density of the cantilever as rho. EI be the flexural rigidity of the cantilever beam, and L be the capital L be the length of cantilever, small l be the length of string. So this is the reference system of the entire model. And as we are putting the model into the earthquake scenario, we are assuming that the movement or the vibration can be in the form of the sinusoidal wave y is equal to y naught sine omega t. So the tension at a point x on the cantilever beam can be due to its own weight and also due to the pendulum mass, which is a function of theta. And we also let's say that the field variable w, which is a function of x comma t for this model. So the kinetic energy k can be due to the kinetic energy of the cantilever beam and also the pendulum mass. So coming to potential energy, the potential energy of the cantilever beam can be due to the bending and also the compression due to the tension. And there also present a term by the potential energy of the attached mass. Firstly, we are variably separating the field variable into different functions which are independent of each other, time and displacement. And coming to boundary conditions, we can see, as we have just discussed, that the gradient at the ground is zero, and the displacement of the cantilever at the ground can be due to the earthquake itself, which is a function of sinusoidal wave. And from Ritz approximation, we can consider the displacement function phi of x can be y of t plus x square and also y of t plus x cube. So finally, our field variable w of x comma t can be modeled into alpha 1 of t into y of t plus x square plus alpha 2 of t into y of t plus x cube. So this is the final representation of the skyscraper models into our kinetic energy, potential energy, and field variables. Thank you.